So guys, in this video we are going to see that how we are going to extract the iron from iron oxide using your Ellingham diagram. Please do remember that in your syllabus we are mainly going to deal with the extraction of iron from iron oxide, copper from copper sulfide, zinc from zinc oxide, aluminium from bauxite ore, and also a leaching process for the extraction of the gold. So one video will be mainly with respect to only one type of ore. So in this video we are mainly going to see the extraction of iron from iron oxide. So as I have dealt with the Ellingham diagram, we have said that of course whenever we have to extract a particular metal from its ore, we need a reducing agent. So for the suitable choice of your reducing agent, our Ellingham diagram plays a vital role. So how does this Ellingham diagram was plotted? It was mainly with respect to that of your thermodynamic principle. In this case, that is extraction of the iron from iron oxide, we are using a reducing agent called as your coke, which is not other than that of your solid carbon. So what is the main reaction that is taking place is basically your iron oxide is treated with respect to that of your coke to give you the iron plus carbon monoxide. This is the thing. Basically, this reaction is taking place in a blast furnace. Of course, there will be a dilemma. What do you mean by a blast furnace? You just remember that it is like an instrument which is used in industries for the extraction of your iron from your iron oxide, which will be seen in this video later. So basically, we know that whenever you're choosing a suitable reducing agent, in order to reduce your metal oxide to a corresponding metal, the reaction should be spontaneous. So of course I have said that in order to this reaction to be spontaneous, it involves two important reactions. First is the reduction of your metal oxide and the second is the oxidation of your reducing agent. That is what is happening. FeO, first it gets reduced to give you as Fe plus half O2. Let me take this one, whatever the delta G I am calculating over here, or form FeO to Fe. Yes, as this one has to be delta G1. Similarly, the other set of the reaction is that of your oxidation of your reducing agent. That is C plus half O2 give rise to CO. So let us take this one as delta G2, that is from C to CO. We know that if this reaction has to occur on its own accord, that is, the reaction should be spontaneous, means what should happen? Overall delta G of the reaction, that is the sum of delta G FeO Fe plus the delta G of CO should be equals to negative. So only we can say that this reaction is possible. Now the question arises that, sir, why did you choose basically the coke as a reducing agent? Of course, there were many, as we have seen in our Ellingham diagram. Even you can have used zinc, you can have used your copper monoxide. But why we are using particularly the coke, it depends upon its temperature condition. That is, when you are seeing the Ellingham diagram for this important reaction, I can just show you that. Yes. So here we could see that this is the curve for your iron to iron oxide curve. Yes. And this is the curve of your carbon to carbon monoxide. We could just notify this from the fourth part or the fourth point of Ellingham diagram. What does it say? The curve of the element's oxide. That element can be used as a reducing agent only to the metal which is lying above it, or only with respect to the metal oxide which is lying above it. Now the question arises, why we have to choose the curve which is above it? So of course here when I am seeing the reaction, what I am saying, first your iron oxide should give out the oxygen. it will be having some delta G. Of course, this delta G is also negative. You could just see over there, iron oxide's delta G is also negative. But what happens with respect to the coke? Coke ka curve is also having some, if I am continuing over here, nearly in the minus 800 part I am getting, which is more negative of your delta G. Since delta G is becoming more and more negative means what? The tendency of the coke to extract this oxygen will be in a greater extent. That is, it will be higher spontaneous. That is the reason we are saying that the curve of your metal oxide or element oxide, such metal or the element can be used as a reducing agent for the curve of the metal oxide which is above it. That is the reason we are choosing it. This is what the explanation it says. As you go down, the delta G become negative. So the tendency of the reducing agent to extract the oxygen from your male metal oxide increases and the reaction becomes more spontaneous. So keeping this one in mind, by using the same form, of course what is happening, we can use the coke as a reducing agent only when it is lying below that of your metal oxide curve. And when does it happening so? Only above the temperature of your 1073 Kelvin. So mainly in this process, FeO can be converted to Fe by using your coke as a reducing agent only when the temperature is greater than 1073 Kelvin. Why is it so? Because after that temperature itself, our carbon or the coke can act as a reducing agent. Because after that temperature itself, our curve of the reducing agent lies below of the curve of your metal oxide. So this is a tendency for all the extraction of your metal oxides to their corresponding metals whenever you're choosing a reducing agent. Particularly, you have to keep in your mind, for the extraction of the iron to iron oxide, we are using the reducing agent as a coke, and it is only used only when it is a temperature is, when the temperature is greater than, whenever the temperature is greater than 1073 Kelvin. Now let us see that how does your industries employ this method by utilizing a suitable apparatus. So basically the apparatus in which we are carrying out this reaction is called as that of your blast furnace. To have a clear view, we can just use your textbook. Yes. So here we could see this is actually called as that of your blast furnace, where you could just see from the top we are introducing our ore. Of course that will be your iron oxide which has been calcined. So before that one I have to mention you that once we have to go by step, that is from earth whatever the ores we have took out, that is first of all what has been done, it has been concentrated using the method of your hydraulic classifiers, that is by a jet wash of water. Since it is an oxide ore, once you have concentrated, that is you have removed all the sand and mud impurities, so then it is subjected to that of your calcination. Since it is an oxide ore, we are burning these ores in the absence of oxygen. Once you have done those two processes, the next process involves which is called as that of your reduction or smelting. So in this process, we are going to extract our main metal from its metal oxide. So that process is done in this apparatus which is called as that of your blast furnace. So from the top what you are doing is we are introducing our ore, the coke which acts as a reducing agent, and a limestone. Remember here limestone acts as a flux. Of course we are going to deal with it in the same video afterwards. What do you call as a flux? For a while you just remember from the top we are introducing our ore, limestone and the coke. So once you are introducing from the top, from the beneath you are blasting the hot air through these passages. So once you are blasting the hot air, what happens? Your coke, whatever which was present, that will react with it, your oxygen, to give you CO2. Okay, so that CO2, whatever it is taking place, if I just say that is C plus O2, it gives rise to CO2. This reaction is an exothermic reaction. Of course, I have maintained a temperature greater than 1073 Kelvin. But this reaction, what does it do? Being an exothermic, it further increases the temperature to nearly 2273 Kelvin. So once what happens, this CO2 has been produced in the blast furnace, it moves upwards. When it moves upwards, what happens? Of course, these layers, that is whatever the walls you could see in this blast furnace, they have been coated with a coke initially. That CO2 once again reacts with this coke and gets reduced to carbon monoxide. And by different sections, you can just see in each and every temperature zones, they have written you certain reactions. So in the different sections, the different reactions takes place in order to for that of your reduction of your metal oxide to your metal, that is from iron oxide to iron. Let us see now one by one. So basically in the blast furnace, we are having two sets of reactions. That is, first one, the reactions which are undertaken at the low temperature, that is in the range of 500 to 800 Kelvin, of course, that is from the top. Then the reaction which is taking place at the high temperature zone, that is of your 800 to 1500 Kelvin. So first let us see that what is happening at the top of the blast furnace, because at that region the temperature is somewhat normal, or we can say somewhat light. So what is happening over there? So basically whatever the ore you are having, Fe2O3, yeah, hematite ore, in the presence of your carbon monoxide that I mentioned you earlier. So the CO2 which was going upward in the blast furnace have come in the contact with that of your overlying layers of your coke, and it has been reduced to that of your CO. So utilizing that CO, what happens about your oxide ores of the iron? First it gets converted to that of your magnetite ore, Fe3O4, it gets oxidized plus CO2. If you balance this, 3 Fe2, 2 Fe3O4. Of course, this Fe3O4 once again come in contact with that of your carbon monoxide to give you that of your Fe plus 4 CO2. Of course, your 4 CO. Once again, your remaining Fe2O3 comes in the contact of your CO to give you what? Iron oxide. This is the important reaction. Plus CO2. 2FeO plus CO2. So these are the three important reactions which is taking place at the lower temperature, that is at the top of the blast furnace. As you're coming down, this FeO now will be utilized in that of your reaction at the high temperature zone. Of course, what happens? C plus CO2, first it is given you that of your CO, what we have earlier, we have explained over here, the same reaction is taking place at the higher temperature zone. Then that FeO plus CO, this FeO which has been produced over here, it is coming under down, which is reacting at the high temperature zone with respect to the of your carbon monoxide to give you iron plus CO2. So here you could see that how our metal oxide has been reduced to that of your metal. So this is the main important reactions which is taking place in that of your blast furnace. Now coming with respect to that of why we used limestone over here is the major thing to be understood. So limestone is here acting as a flux. So what do you mean by this flux? So flux are the materials which are going to combine with like that of your sand particles or some other impurities to form a slag. This slag is actually a mixture of that of your flux plus gangue. That is your impurities. So in order to avoid such impurities in the extraction of your iron from that of your iron oxide, we are using limestone as a flux. In each and every extraction of the metals, we will be using different flux. But in this particular extraction of the iron from iron oxide, we are using limestone as a flux. Let us see how does it work. Of course, we know that limestone composition is calcium carbonate. First, on the high treatment of the heat, it gets a calcium oxide plus carbon dioxide. This calcium oxide, what does it do? The sand particles, whatever it is present, that is your silicates, SiO2, it will combine with it to give you as calcium silicate, CaSiO3. and this is called as that of your slag. So here this is called as that of whatever the calcium carbonate here, this was your flux. Of course, this flux is going to react with that of your gang, that is your impurities. So flux plus gang give you the slag. So if I just choose my diagram once again, we could just notify that of course from the top, which was coming as oxides of the iron, your Fe2O3, Fe3O4, at this stages they are getting reduced to that of your FeO at a lower temperature zone. Once they are coming to the higher temperature zone, what happens, that FeO reacts with that of your carbon monoxide to give you the molten iron. Along with that one, you will be also having the slag form. We just notify over here, this is the part of your molten slag. So this is the some sort of your impurities. So that will be taken out from the blast furnace as a solid waste, and that of your molten iron is just separated from the molten slag, and it is obtained as that of your pig iron. Here you have to remember, so whatever the iron we are obtaining from that of your blast furnace is that of your pig iron. Now the question arises, why it is called as that of your pig iron? Or in simple words, we could just say that whatever the iron we have obtained from the blast furnace, whether it is the high quality iron, the answer is no. So remember guys, whatever the iron we have obtained by utilizing your coke as a reducing agent from the blast furnace is called as that of your pig iron. It is mainly called as such because this iron mainly consists some other impurities like your carbon, your phosphorus, some other elements which are decreasing the quality of your iron. And one most important fact you have to remember, that the quality of the iron increases as the percentage of the carbon decreases. So in this iron, pig iron, we are having the 4% of your carbon. Along with that 4% of the carbon, as I said, you are having your sulfur, you are having your phosphorus, you are having your silicon, manganese, etc., and which is making the obtained iron to be the most impure, and that is the reason it is called as that of your pig iron. Now the question arises, can we obtain a high quality iron from that of your pig iron? The answer is yes. So basically the main thing, if you want to increase the quality of the iron, one important thing we have to do is we have to decrease the percentage of the carbon. We have come to know that in pig iron we are having nearly 4% carbon. So by any means, if I am going to reduce this percentage of the carbon in the iron, of course I am going to get a good quality iron. So soon after the pig iron, the higher quality is called as that of your cast iron. So basically how to obtain this cast iron? Basically whatever the pig iron you have obtained, that is treated with that of your scrap iron. That is treated with that of your scrap iron. Of course, basically it is heated in a reverberatory furnace with using the same content whatever we have done in a blast furnace. So what happens over there when you are doing such things? Of course an iron will be obtained of nearly 3% of your carbon content, which is less than that of your pig iron, and that is called as that of your cast iron, which is having a somewhat higher quality than that of your pig iron. So whatever this iron is obtained, this is extremely hard and brittle, but it is not the highest quality. The commercially known highest quality of the iron is called as that of your wrought iron, of course, which is obtained from that of your cast iron. So how to obtain this wrought iron? Basically we are using a reverberatory furnace similar to that of your blast furnace itself, but instead of coating the reverberatory furnace with a coke, what we are doing is we are coating it with that of your hematite itself, that is your Fe2O3. Of course the same process is carrying out. Whatever the cast iron is there, that is taken along with the coke at a very high temperature. So that coke comes in contact with that of your Fe2O3 overlying layers to give you the iron part plus that of your 3Cu. So this iron whatever you have been obtained, that is very much having the lower percentage of your carbon, and that is the reason they are also called as a malleable iron, which is the purest form of your commercial iron. Here also we are using the limestone as that of your flux itself, which is mainly utilized to remove whatever the impurities which is present in that of your cast iron. So by this process, one can easily extract the iron from iron oxide using your coke as the reducing agent. This coke can be used as a reducing agent only above the temperature of your greater than 1073 Kelvin. Because only at the greater than 1073 Kelvin, we are able to see that in the Ellingham diagram, the curve of your C to CO lies beneath the curve of that of your iron to iron oxide. So on then in that temperature range, your coke acts as a better reducing agent. So in the blast furnace, we saw that of course there will be two temperature sections are there. One which is at a lower temperature 500 to 800 Kelvin and another at a higher temperature nearly 800 to 1000 Kelvin. So the main reaction in the lower temperature I would like to say is this reaction, that is your hematite ore is getting converted to that of your iron oxide in the presence of your carbon monoxide. So this iron oxide is then utilized in the higher temperature zone. Of course, the coke is first getting converted to that of your carbon dioxide coming in contact with the coke is first converts to that of your carbon monoxide. That is going to react with that of your iron oxide to give you the iron. Remember, whatever the iron we are obtaining, that is called as that of your pig iron, which is not the highest quality. This is called as a pig iron because it is having certain impurities like your carbon, phosphorus, manganese, silicon, all those things. And remember, the quality of the iron decreases, the quality of the carbon decreases as the percentage of the carbon increases. Or in simple words, here pig iron is the very lowest quality. That means what? The percentage of the carbon will be at the very highest part. That is the reason in the pig iron we are having nearly 4% of the carbon. So in order to obtain the high quality, what we have to do? We have to decrease the percentage of the carbon, which has been done in respect to that of your cast iron, which is somewhat a higher quality compared to that of your pig iron. So what we have done over there in pig iron, we have taken a pig iron which has been treated with that of your scrap iron, okay, in a very high temperature. Of course, using the coke as that of your reducing agent once again. So we are getting an iron which is having nearly 3% of the carbon. So as the percentage of the carbon decreases, quality of the iron increases. But this is not the highest quality. On top of it, we are having the wrought iron, which is the purest commercially used iron, which is obtained by oxidizing the impurities in a reverberatory furnace, which is lined with that of your hematite. So this hematite, whatever the carbon content is there in your cast iron, it oxidizes to that down as carbon